All right, so here it says graph f of x equals 2 to the x minus 1 plus 3, state the domain, range, and asymptote. All right, well, if we look at this function that they just gave us, can we see what the parent function is? Well, the parent function looks to be f of x equals 2 to the x. And so what have we done here? Well, the plus 3 says we've moved up 3, and this says we've moved right 3. Oh, to 1, sorry, not 3, 1. Okay, moved right 1. Okay, so that's going to be kind of our change we see because, if we subtract 1 here, then that gives us moving right 1. If we add the 3, then we're going to go up 3. So let's say our x's, what happens with x's? Well, it says we moved them right 1. So if we started at 0, our new one is 1. If we started at 1, our new one was 2. If we started at 3, our new one is 4. Okay. Now, if we started at 1 for y, what have we done? We've moved up 3, so we're going to have now 4. If we started 2 and we move up 3, we're at 5. And if we started at 8 and we moved up 3, we're now at 11. Okay, so now let's see if we can attempt to draw this. Okay, so let's say 1, 2, 3, 4, 5, 6. We only need to go to 4. That's good. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's good. So now our 1 and then 4. 1, 2, 3, 4. So that's somewhere about there. And then we have 2, 5. So 2, 5 will be somewhere there. Then we'll have 4, 11. So that's clear to the top. And so that would be about maybe there. And so now what do we know about our horizontal asymptote? It's at the 3. So let's go ahead and do that. So when we draw this in, we don't really go beyond that. So this is going to come down and then get really close again, but not touch there. Now, original one, it was, through that point here when we would go up, but now we've kind of moved it, and now this is our current situation. So we had, the 0, 1 we went through, and then the 1, 2, and then the 3, 8 was about here. So, we had that one to start with, but now we have the new one, which is that. So that's our new graph from our original base. And now what's our range? Our range, well, it's going from 3 to infinity. Our domain, well, it doesn't change. It's still going from negative infinity to or to positive infinity. And our asymptote, well, that was y equals 3. That's why we put that in there first, because we knew we've moved up to 3. And so that was going to be our asymptote. Okay. And so that's how we can look at the vertical and horizontal shifts. We can write out a new table, and then we just plot that new one, and we have what we get for our graph, and then we can write our range domain and our asymptote from there. All right, so here it says we're going to use a calculator to approximate the solution of an exponential equation. So what do? Well, we type the exponential equation into y1. We type the given value of f of x into y2. We graph the function, make sure the window includes that intersection point. That's sometimes a problem. You have to move up and down a lot, so you have to kind of figure what that is. Then we're going to use the second trace button to find the intersection, and that's going to be number 5 is the intersection to find the intersection point, and then we kind of do what we do accordingly. So let's go plot this. All right, so we go here, and it said for y1, plot our actual function. So that was the 7.85, and then it was times 1.15, and that was to the x. And then that was minus 2.27. So that was our first part. And it says set that equal to 4, y equals 4. And then graph it. Okay. Well, we got lucky. It's actually on graph, so we're good. Now we just do second trace, and we want 5. And the first curve is blue, yep. Second curve is red, yep. And we're just going to guess there. And it tells us our intersection point is x equals negative 1.608, y is 4, which we should hopefully get 4 because that's where it's got to be for the intersection. So that means round to the nearest thousandth. Well, that says x is equal to a negative 1.608. So that's the thousandth, and that's all they gave us. So that's good. They wanted it to the thousandth. Okay. So that's how we can solve these graphically. You know, we plot one side over here equal to the y1. Then we plot our other side as y2, find that intersection, and we get our value out. All right, so next let's look at stretches and compressions. So we looked at, left and right, up and down. Now let's do stretches and compressions. So that's going to be our A. So now we have A times B to the X. So stretch vertically by a factor of A if A is, the absolute value of A is greater than 1, okay? It's going to be compressed vertically by a factor of A if A absolute value of A is less than 1. So if we think about that, if A is, 3, then we're going to go up 3 basically for our stretch. And if A maybe is 1/3, just because that's kind of the opposite of that, then we're going to compress it down by 1/3, okay? And we're going to have a y-intercept of 0a, all right? So that's the key here. So a is now going to be 3, and or in this case, it's going to be 1/3. So if we started out as a is 1, and now we have a of 3, we moved up 3. And if we had it at 1, and then we took it times the 1/3, we moved it down 1/3. So this is showing us how that is. So the first one is a of 1. So if we think about that, it's 1 times 2 to the x. That's our red curve, and we get our 0a, which is there. Then if we have 3 2 to the x, well, guess what? We're going to have 3 now. We're going to have 1, 2, 3, and that's where it's going to be. And so then we have the curve kind of drawn in the same manner, but through that 0, 3 point. Now, same thing works with compression. This is really 1 times 2 to the x, so that's going to be our 1, 0 again. Now we're going to take it times 1/3, so we're going to go down to 1/3. That's down here, 0, 1/3. And now our graph is going to be drawn through that point there. So it's going to be down here at 1/3. So we're compressing it down towards the x-axis, whereas here we're stretching it away from the x-axis. All right, so we want to sketch a graph of f of x equals 1/2 4 to the x. All right, so let's choose some points and then we can graph it. I don't know, let's do 0, 1. Now, if we use 3 like we did here, 3 is going to be a huge number. So let's only go to 2 because I think that would be a little better. We don't want to get too big or we'll have a lot of things to measure here. So 0, 4 to the 0 is 1. And half of that is 1/2. 1. 4 to the 1 is 4. Half of 4 is 2. 4 squared is 16. Half of 16 is 8. Now, if we did 3, 4 to the third, that's going to be 64. Half of that's going to be 32. And I don't want to draw 32 lines. So that's why we're only going up to 0, 1, 2. All right. So we have 0, 1, 2. Let's spread it out quite a bit so we can kind of really see the differences. So 1, 2, 3, 4, 5, 6, 7, 8. So 0, 1/2. So we're right there. 1, 2 is about there. And 2, 8, roughly there. And now we can draw our graph. So now it's going to come down and do something like that, okay? And again, trying to draw the smoothest curve through it's ideal. I'm not the best in the world, especially on the computer. All right, so what is our domain, our range, and our asymptote? Okay, well, our domain, it's going to be the same as always. It's going to be from negative infinity to infinity. Now, our range, well, this one we didn't do any shifts up or down, and so it's going to still be 0 to positive infinity. It's going to, never touch that, so it can't have a bracket there, but we can have a parenthesis. And that means our asymptote is y equals 0. Okay. So again, plotting 3 points, we got, fairly decent curve looking thing here. And that's what we want to get for that. Now you could always plot this in Desmos if we wanted to, and get a perfect curve. If we go to Desmos or even to our calculator. So here, if we did that, we would have, 0.5 and then times, and then our 4, and then we would want to have 2, the x, and that's what it would look like. Okay, and again, here's our 1, and so we're at half, so that makes sense. Our 1, 2, 3, and if we go up here, 2, I'm sorry, 1, 2 to 8, that's right there. And so, our graph looks pretty much similar to that. It's just hand drawn instead of nice and perfect like on Desmos. All right, so let's stop there and we'll come back for more.